Okay, thank you. Thank you very much. I want to say this is all a joint project with Paul Seidel. So the thing that we're looking at is sort of the simplest, most naive version of the quantum connection. So what we have is a closed monotone symplectic manifold, meaning the symplectic form is, by monotone, I mean the symplectic form is equal to C1, and the quantum connection is then just the operator which differentiates with the variable q according to this rule. So it's the differential. So the matrix part is the quantum multiplication with the symplectic form, or equivalently C1. And by star q here, I mean the small quantum product. So where one keeps track of the appropriate power of q according to the area of the curve, or equivalently the first Chern class. So even though this is about the simplest thing you can write down, there's some interesting questions about it which are unknown. So here we're going to be looking at its sort of the singularities of the connections. So so you take, there's a grading operator on cohomology, and you can actually use the grading operator to just a simple gauge transformation to simplify the quantum connection a little bit. So so that it looks like this. So at q equals 0, you can see that pretty easily that it has a very simple pole structure, a pole of order 1, and it has so it's a regular singular point with a unipotent monodromy. It's much more interesting to kind of look at the pole at q equals to infinity. So so for that, let's change variables to q equals to infinity, and then if you look in its original form, what you get is sort of what I have in equation 6. So it has this structure right here, but the gauge transformation I made before sort of clarifies the structure again, and so it has the structure of a pole of order 2 times some constant matrix, and then again the grading operator in the pole of order 1. And so the conjecture which I want to discuss is it's in a more general context in Kontsevich, Kotsarkov, Pantev. Let's just call it KKP. I imagine a lot of people are familiar with the paper. The non-commutative Hodge theory paper, and also Galkin, Goleshchev, and Iritani's paper. And so the conjecture that I want to discuss is that it says this. So it says that the quantum connection, so the singularity, this pole of order 2 at q equals infinity, is of unramified exponential type. Sorry. And actually KKP, they make this conjecture from in a more general context. So they make it for not just monotone symplectic manifolds, and not even necessarily algebraic symplectic manifolds, but that conjecture, I think, at least according to some computer calculations, that's false. The case that I actually want to look at is the situation of an algebraic Fano manifold. So particularly when M is a Fano manifold, and it carries a smooth anticanonical divisor. So I won't explain, there's still how to prove this conjecture, but I want to explain a program that I think will eventually lead to a proof of it in that case. So let me sort of define what it means to be to have a singularity of unramified exponential type. So so if you have, so the theory of formal meromorphic connections is a classical subject. So if you take a meromorphic connection, then it's acted on by gauge transformations. So you say that the connection has a regular singular point. That's the simplest kind of singularity. If by formal gauge transformations, it can be brought into the form q to the -1 times a matrix with power series coefficients, so no more poles. And the next simplest thing, if you have a pole of order 2, say, would be this situation of unramified exponential type, where you can formally gauge transform it into a connection which breaks up into pieces, where each of the pieces looks like a regular connection. So this is sort of the regularized version of the connection, and then some constant times the identity in the pole of order 2. So the reason that these sort of connections are relevant for mirror symmetry is the following. So for in mirror symmetry, if you have a connection like this, then so let's say I'm looking at a neighborhood of q equals 0, then actually it's a general part of the general theory of these connections so this is due to, I guess, Turretin is one of the, Lebelt and Turretin, I think, are the names that go with this result, that you can actually extend the decomposition that you have as part of the definition of unramified exponential type. You can extend that to certain sectors in the plane. So it becomes an analytic decomposition. So the sector, you have some angle, as long as it's sort of a generic angle, and then you can extend the decomposition into sectors that have slight angles slightly bigger than pi. So this would be sort of one sector, and then in Dubrovin's conjecture, what you do is you take one sector and then you look at the negative angle, and you get sort of some kind of Stokes matrices. So the analytic, so you have these sectors that of angle slightly bigger than pi, and you have two of them, and then they overlap in some region, and that allows you to define an analytic continuation between their solutions, and the matrices that analytic continuation are called Stokes matrices. And Dubrovin's conjectures is about how those Stokes matrices come from sort of pairings in topological case, or even at the level of the derived category. So I don't have much to say about Dubrovin's conjecture, so I don't want to spend too much time defining it, but basically this conjecture, if it's true, would allow you to state Dubrovin's conjecture more generally than semi-simple, than manifolds whose quantum cohomology is semi-simple. Traditionally, Dubrovin's conjecture is stated for manifolds as quantum cohomology is semi-simple because in that case, the connection is automatically of exponential type. It's easy to see that. Okay, so now I want to try to explain the idea for how a proof of this might eventually look like. So for one possible way. What I want to do is explain. So traditionally, the reason people believe this conjecture comes from mirror symmetry. So let's sort of, I need to explain some basic algebra. So let WQ be the algebra of differential operators in a single variable, and you say that a module is holonomic if it's finally generated, And furthermore, if for every x in your module, there's a non-zero element that annihilates it. So if you have a holonomic D module, then there's some non-zero, there's some polynomial, so that if you localize away from that, you get something, basically a vector bundle with connection in that has singularities in the sense that, in the formal sense that I was discussing before. And it's sort of a standard idea to so what we want to do is sort of place this exponential type condition into a more standard setting. So
excuse me, I am a bit lost. So first of all, this definition is only of holonomicity. It's okay in dimension 1.
Yes.
But it does not cover, there is a more general definition of the holonomic D module.
Yes.
And it allows some delta functions which certainly do not come from bundles with connections. So then I'm
if you remove, so I would say that all those points are, if you have delta functions, then you localize away from that. It's trivial.
Yeah, that's true. But this your last condition, I'm kind of a bit confused with. What does it say? Is it say exactly what you just mentioned, or it says something different? There is P from 1 and Q. What is?
Oh no. So sorry. This is a typo.
P.
Sorry, I wrote this.
It's localization. You add
yes.
one over. Okay, great.
Yes.
All right.
Yes.
Okay. Then it's fine.
Thank you. Okay, so what we want to do is just to make a simple transform. So it's a well-known idea to take the Fourier transform. So we want to think of the differential operator. You make a simple change. So the commutation relation, you can swap the variable in the differential operator. You have to add this negative sign to keep the commutation relation true. But so you have this change between ddq and q, and if you keep the module the same but now regard it as a WT module, that's called the Fourier Laplace transform of the module. And the Fourier transform preserves holonomicity. So, and it's a fact, you can find it in the book of Claude Sabat, probably a well-known fact to people who know this sort of thing, that if you start with a holonomic WT module and you make its Fourier Laplace transform, then you get something which is non-singular on C star. Sorry, you start with a holonomic WT module with only regular singularities. Then if you make its Fourier Laplace transform, then it's non-singular on C star. And furthermore, the singularity at q equals 0 is a regular singularity, and the singularity at q equals infinity is of a unramified exponential type. So it's exactly the kind of module that we get, we expect to get from quantum cohomology. So, let's look at the mirror to quantum cohomology now. So the mirror picture is where you have a proper Landau-Ginzburg model. And then the mirror construction, the thing which is expected to be mirrored to quantum cohomology, is the so-called Gauss-Manin system. So it's defined by taking cohomology and Durand differentials and adjoining a variable of degree 2, and looking at DW twisted differential on Duram cohomology. So this complex of sheaves carries an endomorphism, and which makes the hypercohomology of this complex into a Weyl module. So there's a better way to say this. If you like D modules, you're looking at the D module push forward of this is an explicit model for the D module push forward of the structure sheaf. So from that, you can see that just from the general facts about D modules, you can see that that this will be a holonomic module in each degree. And furthermore, so it's a proposition in this case that this has the structure you want. That it has a connection, that it's exactly the structure you want. Q equals 0. It's regular singularity and singularity of unramified exponential type at Q equals infinity. And the proof of this goes as follows. So, or one possible proof would be to say you localize away from the singular values, and away from that, you can prove that the Gauss-Manin system is isomorphic to the usual Gauss-Manin connection that you know using relative differential forms that you learn about in complex manifolds class. And so by the work of a bunch of people, a very famous theorem, the Gauss-Manin connection, so the thing over here has regular singularities in the if you regard it as a WT module, and since we're looking at it as a WQ module, that implies the fact that it has the unramified exponential type. So so sort of the proof needs a couple of ingredients. So first of all, you need a version of this monodromy theorem here. So that's sort of the big input to the result. And you also need that you can remove finitely many values from A1 to obtain something which is smooth over A1, so that you know that the Gauss-Manin connection actually is going to have regular singularities. And then the third ingredient you need is the sort of Fourier transform relationship between the Gauss-Manin system and the Gauss-Manin connection. So one is regarded as the left-hand side of this is we're going to regard as a WQ module, and the right-hand side as a WT module. So the idea that what we're trying to do here is to take this proof and do it in non-commutative geometry. So what's sort of the non-commutative setup, or the non-commutative version of a Landau-Ginzburg model? So the thing we started with here. So again, we're looking at the situation where you have a Fano manifold which carries a smooth anticanonical divisor, and we're going to take its complement, and sort of this will be an affine variety, and so this affine variety has Floer theoretic invariance attached to it. So it has a symplectic cohomology, which is sort of the version of quantum cohomology for open symplectic manifolds, and it has this a wrapped Fukaya category, which is the Fukaya category for non-compact symplectic manifolds. So so the idea here is that this symplectic cohomology carries a distinguished element theta. So it's not just a there's more structure to the category when it's realized as a complement. It also carries this a non-commutative kind of a non-commutative function on it, which is the analog of the W. So it, and what this class is measuring is measuring how the compactification deforms Floer theory. So the class itself, so symplectic homology, maybe I can draw some pictures here. Okay, so you have your divisor D, and symplectic homology, it's a closed string theory, so it's actually like Hamiltonian Floer homology of the complement. And so you can imagine there's some periodic orbit of some Hamiltonian living in X. So this is our D. We have M, and X is M minus D, and this periodic orbit lives in the complement. And the class in symplectic homology is given by counting certain certain solutions to a deformed Floer equation that are asymptotic to your periodic orbit X naught, and intersect the divisor at least once, or at a distinguished mark point. So it's a map from C to M that solves some kind of Floer equation, and as you go to, say, infinity, it'll be asymptotic to a periodic orbit, and then at 0 it'll pass through it has to intersect you require that it intersects the divisor, but nowhere else. And it turns out that this gives, many people have sort of looked at these sort of classes. So I have a paper on them, and Borman, Sheridan, and Baralgunish. And so this is going to be the structure, the non-commutative Landau-Ginzburg model.
So this theta is sort of a Maurer-Cartan element in some Hochschild whatever complex. So what is it?
Well, it lies in symplectic homology originally, but I don't know. I did something bad here.
Just do not press on leave meeting. Everything else
say
is
got
okay.
Got it, and then go back to where I was. Okay, like this. Okay, yes. So symplectic homology is it's like Hamiltonian Floer homology. So Hamiltonian Floer homology in turn admits closed open string maps to Hochschild homology. So it's like,
yeah, okay, it's written here as C star, so it's written, where is it? Maurer-Cartan.
Yeah.
Theta gives a Maurer-Cartan element. I don't know what is Q theta, but
Q is so theta has degree 0, and so you would join a formal variable Q. And so Q,
because Maurer-Cartan has to be of degree
2.
Well, yeah, well, it depends. For me, it's better to be of degree 1, but you can always shift the gradient, so that's okay. Okay.
In Hochschild homology of degree 2. Okay, so right. So another thing that's sort of going to be relevant to the story is that actually, so this symplectic homology is generated by Rabe orbits along the boundary of your, so you take x being the complement, and you actually excise not just D but a tubular neighborhood of D. So D has some sort of tubular neighborhood that you remove, and so the boundary of that, so the generators of symplectic homology are roughly Rabe orbits along that boundary and critical points of a Morse function in the interior. And in this case of an anticanonical divisor specifically, you can arrange that the symplectic homology is actually concentrated in bounded non-negative degrees. So as a consequence, you know that as well, Hochschild cohomology of the Raphukai category also lives in bounded non-negative degrees. So that's kind of a technical comment, but it seems to be like a shadow of algebraic geometry in non-commutative in Floer cohomology. So this symplectic cohomology, just like Hamiltonian Floer cohomology, it has an L infinity structure. So you can look at parameterized operations parameterized by Fulton. So configurations of points on C up to real translation and translation and rescaling. And you know that gives you parameter space, and you can define parameterized operations, and this element Q times theta gives you a Marc-Cartan element. And you know, just because what I said before, there's actually no it's a Marc-Cartan element sort of for trivial reasons, because there's sort of no negative degrees, so there's no higher possibility for higher powers of Q. So it's just the leading order term actually defines a Marc-Cartan solution. And you can use it using the L infinity structure. You can twist symplectic cohomology, so you can get a deformed differential on symplectic cohomology. And furthermore, because of the boundedness in degree, you're allowed to you can look at polynomials in Q and not just so these expansions actually make sense as polynomials in Q, not just power series. And so the conjecture is which is due to Borman, Sheridan, and Varl-Gunish, is that if you take a Fano manifold, and actually they allow their divisor to be you know, anticanonical simple normal crossings, not just smooth, that this deformed symplectic cohomology actually computes quantum cohomology. So it's not so what they've actually proven is that they have a paper which proves some piece of this. What they prove is that quantum cohomology there's a complex computing quantum cohomology if Q equals 0 part is symplectic cohomology. They don't identify the differential on this complex with any kind of anything coming from L infinity structures, but that's sort of the expectation. And I think they maybe they have another paper where they're going to prove that that hasn't been released yet. In any case, we're going to assume it as a conjecture. There's also maybe a possibility that if you take something which is not Fano, and you can still make this you take something which is Fano, where the divisor supports a positive line bundle, but it's not actually Fano, meaning the complement is still affine, so it still has a symplectic cohomology. And you can ask whether the deformation of symplectic cohomology is going to be finite dimensional once you invert Q.
Daniel, is it kind of instructive to think about these deformed versions as sort of analogs of cyclic complexes?
Yes.
Because especially having in mind your conjecture, yeah, that cohomology of whatever should be probably thought as periodic cyclic complex is quantum cohomology.
Yes.
Yeah, and your Q has degree 2 exactly as Con did. Yeah, all right.
Yes, that it is useful. You have the three versions here, just like in the positive, the negative. I don't know.
Yeah.
Well, I maybe explain a little bit about that towards the end of my talk. So, but we're gonna. So this is sort of a pure question in Floer theory that we're going to assume. So. So when Paul and I started this project, we were hoping they would have finished their project by now, but it's still ongoing, but that's okay. So we sort of took that as an input into our project. But let me try to explain the rough idea. So the rough idea is as follows. So you can imagine that you have a Floer trajectory, so a Hamiltonian Floer trajectory in M, and it connecting two orbits in which lie in X in the complement, and that Hamiltonian Floer trajectory will intersect the divisor a certain number of times, and so if it intersects no times, then it's like the differential in symplectic homology, so it lies purely in X, and otherwise it's weighted by some Q to the D. And you can imagine that you can further degenerate your operations so that these surfaces look like you pull out all of the sort of caps, and then sort of it looks like this, which is exactly what it the sort of operations that come up when you're trying to insert a Mark-Cartan. It looks like you're inserting this Mark-Cartan element into this L infinity structure. So, but the difficulty is that here we've assumed that our periodic orbits actually lie in X. There are also a bunch of periodic orbits. So the Hamiltonians you take are typically actually naturally constant along the divisor. They're like you can perturb them a little bit, but you're still going to have periodic orbits in your divisor. So part of the thing you need to do is sort of prove that in some sense the Hamiltonian orbits which actually lie in X actually, the ones which lie in D do not contribute inside to Hamiltonian to the quantum cohomology. So and that's actually what Borman and Sheridan and Braugunich actually do. So they've sort of have a model for symplectic cohomology which looks like this, and then the remaining step would be to sort of relate it to inserting to sort of splitting it as being an L infinity insertion of this Mark-Cartan solution. So it's sort of a pure question in Floer cohomology, but one that Paul and I have not really worked on because we're hoping they do it. So okay, so as you probably were thinking, you also have corresponding structures just on the open string side. So you can take Hochschild cochains of this wrapped Fukaya category. You have Hochschild chains as well, and it's sort of just a general calculus that Hochschild cochains act on Hochschild chains in two different ways. So you have the Lie module action, and you have it's also an ordinary module by the cap product. And because symplectic homology is so it's isomorphic to this, or it's quasi-equivalent to this, but to this Hochschild homology by closed open string maps, you also have a Mark-Artan element in the Hochschild homology of the wrapped category. So you also have you can do you can take deformations of Hochschild homology and Hochschild homology, and then using that, you finally also, you can do this in S1 equivariant. So using the Hochschild cochain, you also have deformed cyclic homologies and periodic cyclic homologies, and as well as sort of part of the theory of cyclic homology is you have a Getzler connection. So because there's a parameter Q, you can differentiate with respect to Q. And so what we want to do is to take we want to define the noncommutative Gauss-Manin system, so the analog of the Gauss-Manin system, to be this, this should be periodic cyclic homology. So I'm looking at the homology of this deformed module here, with its U connection, with its Q connection. And our result with Seidel is the following. So it says that if this Bormann-Sheridan-Browgunish conjecture holds, then this Gauss-Manin system is holonomic WQ module of exponential type. So one thing that I should mention is in order to really bring this back to quantum cohomology, that you can construct the Gauss-Manin system purely also in terms of S1 equivariant Floer cohomology, by constructing sort of Floer theoretic analogs of Getzler's connection, and this is very similar to a paper of Seidel called Connections in Hamiltonian Floer cohomology. And to finally complete the whole program, what you would need is to prove that this S1 equivariant deformed symplectic cohomology is isomorphic to quantum cohomology with the connections. So it would be an S1 equivariant version of this Bormann-Sheridan-Browgunish statement. So it's a long way to go to actually finish the proof, but hopefully this is a promising program. So I want to explain how some ideas that go into the work with Paul, the proof actually. What I was saying was the ingredients which are needed in the algebrogeometric case are this Gauss-Manin system, which we now have the non-commutative analog of it. The next thing you need is an analog of the Griffiths-Grothendieck monodromy theorem. That actually exists, so that's due to Petrov, Weintraub, and Vologodsky. And what they prove is let R be the algebra function on smooth irreducible affine curve, then and you have a DGA which is over that R, and it's free as an R module. So let's say that, just mimicking usual definitions, A is proper if the cohomology will be finally generated as an R module, and it'll be smooth if it's perfect as an A tensor, as a bimodule, but with keeping in mind the R linear structure. And the monodromy theorem that they prove is basically that if A is a smooth and proper DG algebra over R, then the Getzler connection but now viewing it as a module over R. So this would be sort of using vector fields on your affine curve, that has only regular singularities. So that exists already, and then another thing which exists is it's also known that that if you view the Rapp-Foucault category as a fibration over R, so you can see the input into the theorem is you need that, first of all, that your category is proper over the base, and that's actually a known thing. So if you take this element theta, it actually is a generator for the symplectic homology in this case, for a smooth anticanonical divisor complement. And furthermore, the Rapp category, the Rapp-Foucault category, is proper over C adjoins theta, meaning if you take Lagrangian Floer cohomology between any two Lagrangians, any two conical Lagrangians in this Rapp-Foucault category, it becomes a proper module over, it becomes a finely generated module over C adjoins theta. I can maybe explain a tiny bit about, well, maybe at the end I can come back to that point, but because that may not be so obvious at first, but so by obstruction theory, it's very not too difficult. Obstruction theory, you can prove that that the Rapp category is actually going to be Morita equivalent to a DGA, which is over this C adjoins theta, and in such a way that this Mark-Artan element will just be Q theta. So you can simplify it down basically to the setting of this theorem, and that again uses the fact that Hochschild cohomology is concentrated in non-negative degrees, but the main things you have to worry about to apply the theorem is the Getzler, so the monodromy theorem requires also that the family be smooth over the base, and be a smooth fibration over R, and you also would like, finally you would like some sort of Fourier transform relationship between the Gauss-Manin connection in the theta or t direction and the Gauss-Manin connection in the q direction, which is what we actually care about. So these are the two steps that are sort of missing. Let me actually I think in terms of my timing, I did want to explain a little bit of why this is I do have time to explain a little bit why this is a proper category. So let me actually, am I supposed to talk for 50 minutes or an hour? I wasn't sure. What was the?
Yeah, you can talk for at least for an hour. If you need to speak a bit longer, that's still okay.
Okay, let me actually then explain because I was thinking 50 minutes, but I was rushing a bit. But I have time to explain this properness of the wrapped category. So the idea here is so the statement that the wrapped category of X is proper. Why is it proper over C adjoins theta? There's some sort of pretty simple geometric idea there. So if we have an anticanonical divisor D, then a tubular neighborhood of it actually looks like is a circle bundle over D. So a tubular neighborhood of the divisor is its boundary is a circle bundle over D, and roughly speaking, theta corresponds to the Rabe flow along the boundary is periodic. And roughly speaking, so this count of so as I was saying, the symplectic cohomology is generated by Rabe orbits. So you have periodic orbits which wind once around the divisor, periodic orbits which round twice around the divisor, and so forth. So the periodic orbits actually look like copies of SD indexed by some integer D bigger than 1. And you also have sort of some critical points in the interior of the manifold of some Morse function that don't really matter for this story. And so this element theta, what does it look like? So to lowest order, so there's a small sort of solution which lies very close to the divisor, which winds once around, which is asymptotic to orbits which wind once around the divisor. So roughly, so at least to lowest order, what this element theta looks like is it basically corresponds to Rabe orbits that wind once around the divisor. And if you have so theta roughly corresponds to Rabe orbits. And similarly, if you have now two Lagrangian submanifolds, and you think about, and they're conical, so you think about what the chords are between two Lagrangians. So you have two Lagrangians, say some L0 and L1, which both lie on the boundary. So, well, their chords also have sort of a periodic structure. So if you have sort of short chords that don't wind around the divisor at all. So you have short chords. And then you take that and you take the short chord and you can kind of glue onto it a Rabe orbit to make a new chord. So so every time you have a short chord, you get a whole family of copies of chords which wind around the divisor d times. So for every short chord, say y, you also obtain yd. And the theorem is roughly that the action of symplectic cohomology on chords is like at least to lowest order taking y to yd. So the Hamiltonian Floer cohomology is kind of generated by, as a module over C adjoins theta, it's generated by the short chords, of which there are always finitely many. That's sort of so there's sort of a very, all I want to sort of explain is that there's sort of a very simple geometric reason why the wrapped category is proper. The actual there's some analytical details to make it rigorous, but the basic idea is fairly simple. So coming back to these questions, so I want to find a polynomial where after I localize, I get something smooth, and then I also want to prove sort of a Fourier transform relation. And these two things are just purely algebraic facts. So the algebra, so I'm in the situation where I have an algebra with some just a central element, let's call it theta or w, doesn't really matter. Then I can, to calculate the Hochschild homology over C adjoins T, I just the C adjoins T linear Hochschild homology, I replace it by a cofibrant resolution. And then there's a proposition that that in this situation there's kind of a smaller model for the Hochschild there's a smaller bar complex that resolves the diagonal as a module over AT as a bimodule. So I'm not going to explain exactly what it is. It's sort of a simplified version of the Kožul-Tate resolution, which is in Pragel's thesis. But just using this sort of resolution, you basically it solves all of the sort of these two algebraic problems that I was explaining. So the statement is that using this Kožul-Tate resolution, you get an isomorphism actually between the deformed Hochschild cohomology and the A1 linear Hochschild cohomology, and the same thing for the Hochschild homology. Sorry, it should be Hochschild homology. So the outcome is the following proposition, which is if you have an A and a theta, which and some non-zero polynomial, so A should be smooth over your ground field, and there should be an element in deformed Hochschild cohomology, which so that if you take q to the m and multiply it by this polynomial, that vanishes for some sufficiently large m. So in other words, if you localize by some polynomial, q to the m should become a nilpotent element. Then you can show that actually your localized DG algebra will be smooth over over this localized polynomial ring. And that's going to be, so that's one part, that's going to be one sort of key ingredient. The way that we want to apply this to the setting of quantum cohomology is if you believe that after you localize, in our case, sort of the localized, so HH star with Q localized, so Q plus minus is going to be, if we assume the Borman-Sheridan conjecture, that'll be isomorphic to quantum cohomology. So in our case, P of theta will be exactly the characteristic polynomial of the action of theta on whatever theta corresponds to, which is expected to be the first Chern class. So whatever theta, so it'll be it's expected to be the eigenvalues of C1 acting on quantum cohomology. But if you remove that, then away from there, this module will be a HH star sub Q without localization will be torsion. So basically the upshot is that we, at least if you assume the conjecture, that away from the eigenvalues of the action of C1 on quantum cohomology, we get a smooth fibration. And then the second part is this Fourier transform relationship. So using the resolution, you can also prove the Fourier transform statement in this form that the cyclic homology over K adjoins T corresponds to the negative part of the cyclic homology. Sorry, the Q negative part of cyclic homology, but where Q actually corresponds to the differentiation in the T direction, and differentiation in the Q direction corresponds to T. So so here, if you assume those, I'm about to finish. Don't worry. So if you assume those, then what you do is you find your polynomial, which in our case will be again should be the characteristic polynomial of C1 acting on quantum cohomology. You get something which is a DJ algebra, which is smooth over the localized part, which makes this cyclic homology, the deformed cyclic homology, localized and then U completed. So this corresponds to U completion. Also acyclic. And then what we have is that the negative powers of Q by the previous theorem, those correspond to the Gauss-Manin system. So that's sort of what this slide I rushed through says. And because this thing is a cone between the negative and the positive part, because it becomes acyclic, that means that you've identified the Gauss-Manin, the localized Gauss-Manin system with this Fourier transform of the Gauss-Manin connection. So that gives sort of the last ingredient in the algebrogeometric proof of the exponential type on the B side, and we've translated to the A side. So I think that's everything I wanted to say. Probably it was a bit fast at the end, but thank you for your attention and for the invitation. So
all right, thank you very much. Are there any questions? Yeah, I have some kind of slightly maybe tangential question, but it's related. I hope so. For the conventional Landau-Ginzburg, there is a corresponding perverse Schober, and with Kapranov and Sukhanov, we kind of categorified everything, including the Fourier transform, and in particular this theorem, classical theorem that Fourier transform of D module with regular singularities, kind of all the regular singularities in the finite part can be absorbed by one irregular singularity at infinity, so we categorified that as well, but we did not work with symplectic homology at all. So I'm just wondering whether it's possible to categorify it to something like perverse Schober on the line. I mean,
it looks like you have so you have this for us, it's sort of, you have a family of categories over A1, and you have a finite number of critical points, and then when you make the deformation, you instead, so you have just the wrapped category, and it's a fibration over A1, but and then you make that, you look at the deformed category, and that has at least when you take its Hochschild cohomology, seems to have the structure you're talking about. It seems to give the irregular singularity. So so there you have a, maybe there's just some general result about, you start with something with a category with certain conditions over C adjoins T, and then you look at the corresponding deformation. That sort of,
yeah, maybe, yeah, that's what I thought during your talk, but actually I don't know, because there might be some technical difficulties like this U completion which you mentioned at the end. I mean, some technicalities which prevent from just straightforward deformation of what we already have.
yes, yeah. I mean, this at this stage, I should say that we actually use this is actually, for example, to resolve this kind of problem, we use the closed string, the S1 equivariant symplectic homology construction of the Gauss-Manin system. So it's not a purely, to deal with this last point, it's not a purely algebraic argument. So
yeah, well, that's
so it becomes sort of
interesting. Yeah, it's really interesting, because you know our motivation was partly physics. There is this paper, actually it's not paper, I think it's a book by Gayota, Moore and Witten, something algebra of the infrared, and basically something in physics language. They speak about this massive two-dimensional n equal to 2 theories, for which Landau-Ginzburg is an underlying mathematical structure, and they constructed some what they call algebra of the infrared, which in some sense it's sort of an algebra of an operand, and we constructed kind of, we categorified their story. I mean, it's in the archive. I don't remember, maybe a couple of years ago. Yeah,
it's you, Kapranov,
and Sukhanov. It's three authors. It's kind of, it's maybe a bit It's like 150 pages. It's not an easy reading, but in the introduction, I think we explain what's going on, but it's categorification of this algebra of the infrared, which means that there is an extra structure related to this Landau-Ginzburg, which we discussed. And there is a lot of nice combinatorics, like combinatorics of the secondary polytopes associated with polygon of critical values of Landau-Ginzburg. And so I'm just wondering what's deformed, I mean, this non-commutative, whether it can be kind of added with a little effort, or it's really another project.
Yeah, I don't know.
Yeah. But,
know.
yeah, but
I'll definitely look at your paper.
Yeah. Okay. More questions?
So you said that this main conjecture might not always be true.
Oh yeah, this is sort of a the latest news. Well, yeah. So it's the latest. I mean, we're not sure. I mean, but also I'm not involved. It's my collaborator. He's very good with computer code. So there's actually one example of precisely only one family of examples of monotone symplectic manifolds, which are not algebraic, that are actually known. There's only one kind of construction, which is due to Reznikov, and then Fine and Panov. It's like a twistor space over hyperbolic manifolds. So it's like a certain 12 manifold, I guess, would be the case that we're looking at. Anytime you have a hyperbolic manifold of even dimension, it has some kind of twistor space, and sometimes you get monotone symplectic manifold. I guess you always get a monotone symplectic manifold from it, but they're never Kähler. And what so Johnny Evans actually computed their quantum cohomology, and Paul has a computer program that proved that, well, using a computer program, he calculated that they don't have unramified exponential type. So just as sort of an evidence that this approach of removing the divisor and viewing it as a deformation is sort of maybe the right point of view. So you obviously can't do that, and if you just have a monotone symplectic manifold that's not algebraic, you can't. There's no ample divisor you can remove. So this seems to be the right conjecture seems to be for monotone symplectic manifolds. You could maybe ask the question about algebraic non-Fano varieties, but then you have problems with convergence of quantum cohomology. So it's a little bit harder to formulate the conjecture. KKP, they make the conjecture because unramified exponential type is part of their definition of non-commutative Hodge structure, but they say it might not be true for a non-algebraic manifold. So that seems to be the case. But we're still, I mean, Paul is still verifying it. So it's not yet an official result, but it seems to be that you only algebraic manifolds. Yeah, so that's all I was alluding to, is that there's some calculation, an explicit example of a non-algebraic monotone symplectic manifold that we think doesn't have unramified exponential type, but still checking it out.
Okay.
More questions? Last chance. All right, if there are no more questions, so Daniel, thank you very much for very interesting talk, really.
Okay, thank you so much.
Okay. Thank you. And
Bye-bye.
this is it for today. Bye.